Good afternoon, everyone. So today's I'll be talking about the overview of geospatial technology applications for the water sources, and myself, Dr. Praveen Thakur. I am the head of Water Source Department and also faculty at Institute of Remote Sensing, Dehradun. So this is the overall outline of the presentation. So first, I will cover the basic introduction about the global water cycle and how that water cycle is distributed over the Indian continent, and what are the present status of water availability and water use, and how the remote sensing technology can help us to quantify the various components of the hydrological cycle more effectively, and addressing the key gaps of spatial and temporal resolution, followed by the some basics of imaging spectra for water and snow, and some applications of various remote sensing satellites. What are the remote sensing satellites which we use to map, monitor, and manage the water sources, including the surface water, the snow, and also the groundwater component. And the integration of all these data sets is done in a GIS environment, and digital elevation model and the hydrological models also play a key role where this satellite data is ingested for the better management of the water sources. And followed by this, all data sets have been created in a single web platform, popularly known as the India Water Source Information System, which was a joint project between Central Water Commission and ISRO. And then few examples related to surface water, snow, glacier studies, and the irrigation monitoring, and some of the advanced Earth observation satellites covering the hyperspectral domain and the radar for the water studies, followed by how we quantify the various components of the hydrological cycle using the satellite data, and how we combine the field measurements for improved the calibration, validation, and further feedback to the retrieval models, and few followed by the case studies, few case studies in the geospatial technology applications in the water sources. And lastly, I will cover the what are the future sensors and the satellite missions which are critical for the water security. So if you see our Earth, we call the blue planet. The surface water is almost 71% part of the Earth's area is covered with the water. However, this water is majority saline water, almost 97%. Only 1% of the total water is the fresh water. Out of that 1%, almost 70% is locked in terms of ice in the polar regions in Arctic and Antarctica, and some minor component in the mountain glaciers. For second largest component is the groundwater, constituting about the 30% of the water, and the water what we see in the atmosphere, the flowing water in the river system, that constitutes approximately 1% of the total water, with the lakes and the swamps dominating the water presence. And if we see the our natural water cycle, we have sun as the source of energy, and due to the rotation of the earth and the movement around the sun, we have the different seasons, and also this movement of the earth and the sun energy relative to the given latitude and longitude, it derives the energy cycle and the water cycle. That energy leads to the cloud formation, and those clouds move all from the oceans to the land area, and then once the typical meteorological conditions are achieved, they will condense and the precipitation will be falling. This precipitation in the higher reaches, or the time, the criteria, that is the critical temperature, when it reaches below 0 degrees Celsius, it will fall as a snowfall, otherwise it will fall as a rainfall. And this precipitation, after getting saturating the surface, it will infiltrate, and then it can rejoin as a return flow, and also through the interflow and groundwater flow it will feed into the river system, and some part of it will go as a overland flow. So this is the natural water cycle. And if you see the water balance equation, in the input minus output term, we have added the irrigation. So from where it has come? So this has come because we humans, we change the water cycle. We make the reservoirs, dams, and then we use the water, and then we also reuse the water. We both quantity and the quality is affected by the human water use. So most of the time, most of the river basins or the watersheds, we do not have the natural water cycle. At some place in space and time, we are changing this natural water cycle, which gets signature in terms of the images what we see in the satellite images. If we are making a dam, if we are making a water treatment plant, or if there is a pollution in the river system, so to all those changes in the natural water cycle can also be seen from the satellite data, and then we can quantify both natural as well as the man-made changes in the water cycle. And if you see the total water availability wise, almost 4 billion BCM is the this 4,000 cubic kilometer cubic cube meter is the quantity which is available from the precipitation, with Western Ghats, Eastern India, Himalayan region, Central region, they have the sufficient rainfall, and almost 75% of this precipitation will fall during the monsoon time period. And if you see the total countrywide statistics, we get approximately 1160 millimeter of the rainfall, with the number of rainy days between 5 to 150, and average amount of percentage of global share in terms of the water sources is 4%. And population wise we are higher. That is why if you see the per capita per water availability, here it is presently this 2025 1093, and in by 2050, because population is increasing, it is going to increase by 1450. So we have the similar water sources, but due to the population increase, there is a pressure on the per capita water availability. So that is why we need some information or technology which can give us the better quantification of the water sources, and then also give us the scenarios, for example interlinking of rivers, which can reduce this deficit between the availability and the demand of the water sources. So from 1951 to till 2051, so this is the per capita water availability. Earlier, because water was same, only population is increasing. So this is the from 2011 onwards, we are seeing our country, some of the regions, especially central and the western India, is coming under the water stress conditions. And to observe this, we have from ISRO side, we have the suite of the satellites covering the land and the water sources, where in the optical domain, we have this resource sat series of the satellites having list 3, list 4, and AWIPS covering 5 to 56 meter of the resolution, and the resat 1A, now known as the Earth Observing Satellite EOS 4 series, which works under the all weather category, having resolution of 2 meter to 30 meters. And for the cartography and for the elevation information, we have Cartosat 2, 3 and Cartosat 1 series. And for the weather and climate, we have this ocean, this INSAT series, and the Megatrophics, which is dedicated to the weather. And for the water level, we have the Saral Altica. So we have different set of satellites which cover from some meter to the kilometer range, and covering from a few minutes to the 24 days temporal interval. And not just ISRO, these days we have the satellite from the other global satellite providers, for example Landsat from NASA, and US, and Sentinel from under the Copernicus program of ESA. And more recently, the private companies are also contributing to the satellite technology, not just in earth observation but in the navigation, communication. And there are more than 4,000 plus orbiting satellites which are giving the various set of space information. Now the basics of the imaging spectra, if you see here, so this is the basic spectra of the water. So pure water will be having dark blue to black appearance, because in the visible domain only it will reflect up to 5, 10, or maybe 12, 13% if it is turbid water. For the clear water, it will be absorbing most of the energy, whereas if you see the vegetation and the bare soil, it has the much higher spectra or the reflectance. And the reverse will happen in case of the snow, because it is frozen part. And if you see the visible spectra, from green to NIR to the SWIR, it is highly reflecting, almost 80% or higher than that. And in 1.5, 2 and 2.5 micrometer only, it is absorbing the light. So these two examples, one upper Chandra basin having the pro-glacial lake in Samudra Tapu here, and this is the snow, and white patches what you are seeing is of the clouds. Clouds will have the higher reflection irrespective of we have the SWIR band or the middle infrared. And the bottom image is of the Tehri Dam, where it is shown for one of the dates, and this is the Bhagirathi river, this is the Bhilangna river. So, two extreme cases, one having the high absorption and less reflectance, the second case of the high scattering, less absorption in the visible and NIR is the key characteristics of the surface water and the frozen part, that is snow and the glacier. So, these two characteristics are generally used to map surface water and the snow cover. And depending upon the spatial resolution, for example, if it is AWIPS data, so the mapping scale will be 2,50,000, and it gives the high coverage and temporal resolution. And if you are using the list 3 data, and mapping scale will be 1 is to 50,000 scale, and the various reservoir monitoring, command area mapping, flood mapping, it will be used. And list 4 data, if you are using up to 10,000 scale to map the small structures like ponds, check dams, and field level crop mapping. Cartosat 1 data to 1 is to 5,000 maps, and also to generate the digital terrain model, digital elevation model. And Cartosat 2A, B3 for the higher resolution 3000. If you want to go further, better scale 1 is to 1000 or less, you can also employ these days the drones for the site specific survey. And all these data sets, they are available in the Bhunidhi portal. You can browse and order up to 5 meter. It is freely available to any citizen of the country. You need to create the username login, and from the Vista and the Bhunidhi planner and from the orbit viewer, you can also see when and where is the satellite pass. And if you want to see simply the swipe without downloading, you can in near real time you can see the various images. So, and in the next versions, the online data processing facility, popularly known as the Code Lab, will also be made available to the general users of the Indian EO data. So, from the water sources, as I told, we study it for the precipitation, whether it is snowfall or the rainfall. The water body mapping, the reservoir, lakes, or during the flood seasons, the snow cover and the glaciers, including the parameters, evapotranspiration, which uses the various combination of land surface temperature, albedo, LAI, the water level from the microwave based altimeters or the imaging SAR data at various temporal resolutions, the soil moisture using the microwave remote sensing, both active and passive, topography from the photogrammetry, radargrammetry, and the associated parameters, and the water demand, that is the total crop acreage, crop water requirement, and irrigation requirement, and also the drinking water sources. So there has been sufficient literature available which gives you the summary. This is one of them, where the rainfall, snowfall, what are the possible instruments. So I'll be covering one of each examples in the subsequent slides, how we use the global precipitation measuring mission to measure the precipitation in terms of rainfall, snowfall, and then how we quantify the evapotranspiration, runoff, snow cover, snow density, soil moisture. So for each of this, I will be giving the example in the subsequent slides. So these days we have the dedicated satellites to cover some of these parameters. And to summarize the all the applications in the water sector, so what we see, you see in this image is the typical watershed shown in the black line, and this is the Dehradun city, which is sitting on the ridge line. So the water to the east of the Dehradun, it will flow to the Song river, which is a tributary of Ganga river. Water to the west of the Dehradun through the FRI and other areas will flow to the Yamuna river through the Asan river catchment, and it will meet at the Paonta Sahib. So through this technology, we are able to delineate this watershed boundary using the digital elevation model in the GIS. So that is why we can, in the first bullet, I have shown hydrology at multi-scale. That means if you want to see the water balance at the city level or at the sub watershed level or at the watershed or the basin level. Using this technology, we can do this water balance. And the second component is hydraulics. That means how the water is flowing through a river system. For example, this is the Asan River, or if you get the very high resolution data of the Dehradun city, each individual pipelines, you can do the hydraulic modeling of the water distribution system, for which I will also be showing one of the case studies. So from urban water to the river systems, hydraulics is possible. And at this particular area, what you are seeing is a Asan barrage here. So this is a Asan barrage. So for example, if you want to design the barrage, so you need to know the how much minimum and maximum flow will be there. So for the design flow, the first criteria is you should get the watershed area and the peak flow. So such GIS and the integration of RS data will give you this design flow and the flood scenarios. And the basic computation of length, area and volume, for example, length of the river, length of the canal, what is the area of the water, what is the volume of the water. So those computation can also be done. And here what you see in the natural color composite, the dark green represents the forest area. This is the moist deciduous. On the south of the ridge line, it is the dry deciduous. The light green shows the agricultural area. So and then this blue line here is representing the flow line. And this also is one of the groundwater boundary lines. So if you dig the well, you should get the water at this particular level of the river. So this image also shows the close interaction of surface water and the groundwater. And the last point, for the irrigation water management, we need how much water crop will use. So from such time series of the satellite data, both optical and radar, I can quantify whether this is a rice crop, wheat crop. And then we have a dedicated center in Delhi, MNCFC, so which quantifies this at country level. And once I generate the time series in a given cropping season, I will be able to use the crop coefficient or the evapotranspiration using the land surface temperature to estimate the crop water requirement. So it is a and also we are able to map the canal networks and the various groundwater wells. So it is also a key component for the irrigation water management. So on the left hand side, what you see is the integration: hydraulics, hydrology, groundwater, environment in a GIS environment. So this is how we do all the water sources applications by combining satellite data and the GIS with the various hydrological, hydrodynamic, groundwater and the environmental models. So this is again the summary where what you see is a typical watershed. Watershed, as you see, is a natural unit draining to a common watershed. So this is a Asan watershed which is draining to the Yamuna river at meeting at Paonta Sahib. So then this is a 2D image. So what we see in the reality is the combination of raster data sets and the vector data sets, and we want to represent the real world in a virtual world. And these catchment characteristics, they are geographical in nature. That means they vary spatially with and time. And the physical characteristics such as the soil, land use, land cover, drainage, elevation, they predominantly measuring changing in the space domain, whereas the meteorological hydrological characteristics, they change both space and time. For example, rainfall, temperature, humidity. And if you combine both of them into the GIS and add the time factor, then it becomes the total virtual system where entire catchment is represented in GIS, and its dynamic simulation of the various components can be done in a integrated hydrological hydrodynamic model. So starting our journey from the top of the river, because we are in the Himalayan foothills. So the Ganges River, what you see in the Rishikesh, it comes from the Gangotri Glacier. And glacier by definition is a moving river of ice. So what you see here is a animation where we have added the cloud-free images on annual or more than decadal time scale. And what you see here, the ice on the Gangotri Glacier moving. And here what you see is the gomukh, which is the snout from where the liquid water starts, the ice ends. So apart from this one, you can see this in the single bands, for example in the visible green, red, NIR, and in the swir band. And then if you make the FCC, so this is how our headwater catchment of Ganga river will look like. So what you see here is a ridge line, Chaukhamba here, and this is the Bhagirathi headwater stream of Bhagirathi river. And what you see on the right hand side of Chaukhamba is the Alaknanda river, originating from Satopant and Bhagirath Karak glacier. Here we have the Badrinath, here we have Gomukh, Bhojbasa, and downstream of this we have the Gangotri temple. On the back side of the Gangotri glacier, this particular location, we have the Kedarnath, where we have the origin of Mandakini river, plus there are other parallel rivers which are flowing. So all this river system, Alaknanda, Bhagirathi, Mandakini, they will all flow and they both will meet at the Devprayag. So the headwater catchments is represented by the snow and glaciers and the meadows. So what you see here is a glacier, the snow in terms of the cyan color, and the glacier, here we can see some blue dots also, which are nothing but the supraglacial lakes on the surface of the ice. So this is August September time image when the seasonal snow has melted and the base glacier is visible. And during the winter time period, this entire area will be covered with the snow cover. So it is not just that Gangotri was here, but surrounding area, if you see this Kali Nadi or Yamuna Nadi or Byas, Satluj, Chenab, Ravi, Jhelum, Indus, so they all have this kind of glaciers, and seasonally, like the winter season is currently on set for 25-26. So they have this almost 20% of the minimum snow cover and maximum going up to 60%. This above graph is for the Himachal only. And these basins will have various minimum and maximum snow cover depending upon how much permanent glaciated area we have. So in terms of the water availability, these headwater streams, the first component which contributes is the snow melt runoff, which constitutes almost 30 to 60%, followed by the glacier melt, rainfall runoff, and the base flow. And we observe this both from the satellite data, which is in optical domain as well as in the radar domain. So in the winter, the same Gangotri glacier will be covered with the snow, whereas in the radar, because it is able to see through the clouds as well as through the dry snow, so you can see the underlying supraglacial lakes and the debris cover and also the clean ice. So the date of this is reset FRS2 data, and this is Landsat 8 data for the same date of 18th February 2014. And this is the Tihri Dam in 2000 when it was under construction, and after the construction the full water impounding has been done. And for the regular monitoring, we use this normalized difference water index, green minus NIR band divided by green plus NIR, and then we represent the total water spread area. So one of the dates, it is almost 24 square kilometer of the water spread. So for doing water mapping, we have this portal, which is popularly known as the Water Body Information System of India, hosted at ISRO NRSC website, where all the optical and radar data is integrated, and you simply click on any of the major water bodies, you can generate the total time history. And on globally time scale, you have this global surface water explorer, which is available offline as well as it is available in the Google Earth engine, which can be used to estimate the spatial temporal changes in the water occurrence and other matrices of the water sources. And apart from this, if you want to quantify how turbid is the water, what is the turbidity in terms of NTU, that is quantification, you can use the hyperspectral data. This is one of the example from Chilka Lake, where our field has gone with the spectroradiometer, collected the spectra, and then correlated it with the every NG data sets and generated the various this spectra using the spectral matching technique to generate the quantifiable water quality parameters, in this case the turbidity. And similarly, in case of the floods, the entire area will be covered with the cloud, so optical data may not work. So what we use is the radar data, due to the radar being in the microwave domain, and in the microwave water is a highly scattering surface due to the polar nature of the water molecule. However, our most of the radars, they work in the side looking geometry, So although highly scattering, but roughness wise it is very smooth. So as compared to the other natural water bodies, it reflects away from the sensor, and that is specular reflection. So what you see here in the border of Meghalaya and Bangladesh and in the main Assam, so we have the specular reflection, which gives us easy way of quantifying or the identifying the water pixels, whether flooded or the pre-flood water bodies. So this is for 2008 Kosi floods in the Bihar, when there was a breach at the barrage in the Indo-Nepal border. It was a long duration flooding where the radar sat data and terrasat data plus cloud-free optical data has been used to quantify and monitor the progress of the floods due to breakage of this barrage. And this is for 2023 Delhi floods using the reset data. In the bottom corner, this is Yamuna. In the top, in the Luxor region, near the Bijnor, where we have the barrage. So this area is also frequently flooded whenever there is a heavy flood. And if you zoom to this particular area, so the natural floodplain of Delhi in 2023, you can see entire area is under the water. And the same way we can also use to monitor the mountain hazards, for example the GLOF. So in 2023 4th of October, we have this landslide, and then that triggering, and also there is a calving of the ice in the lake, so due to which there is a breakage of the lake and causing the huge damage in the downstream area. So both, this is the optical data pre and post, this is the radar data. And recently India and US, they have launched the NISAR datasets, and India is taking the lead in the NISAR S-band datasets. So you can see most of the SAR sensors, they are working in the C band. However, we have this S-band SAR data. You can see in the C band, the subsurface vegetation and the moisture is not that much enhanced as compared to the S band. So because S band is having the higher wavelength as compared to the C band, and it is more sensitive to the moisture and the shrub and the vegetation as compared to C band, you can clearly identify areas with the floodplain vegetation and the higher moisture automatically highlighted in the NISA data as compared to the Sentinel C band data sets. And this is below the Bijnor barrage, and this image is of the above the Bijnor barrage, where we have one natural this wetland has been constructed here. This is Sentinel VH data. This is NISAR S band RH data. So you can easily identify, especially the floodplain areas, both for the tributary as well as for the main Ganga river. It has been very clearly marked in the NISAR data sets. And these days all these data sets, size wise, they are huge, so it is practically difficult to do the state level or the regional level flood studies. So we use this Google Earth engine, and in future also our NISA data will also be available in a cloud platform. So if you do this data, so for the state level using the threshold or any machine learning algorithm, you can do the full state level flood monitoring. And because flood is a most recurrent and commonly occurring natural disaster, so there are some commercial companies, for example ISI is one of the companies which has a dedicated flooding team, which they use to combine with the high resolution flood extent map, followed by the flood depth and the elements at risk, by integrating the various high resolution 2D and 3D data sets. And they have a dedicated team of hydrology and meteorology experts who keep watch over the global extreme events and then provide flood information as a service to the customers. And in the mountainous region, sometimes we are not able to see immediately due to the various effects, for example clouds in the severe weather or the layer shadow in the radar images. So generally immediately after the flood we search for the cloud free images. So this is for the Badrinath area. In 2013 we had the very heavy flood in this particular area, and there was a big damage to the hydropower section. This is the Valley of Flowers, where there was a big parking lot which washed away. So before and after images, we can see which are the river valleys which got the highest damage and which may have received the cloudburst. So this valley is not that much widened. However, this Valley of Flowers and this particular valley, not the main Badrinath valley. So this received heavy rainfall, and there are some signatures of landslides also. So there are what we call the cascading of the hazards. So there is a cloud burst followed by the landslide. There is a temporary ponding of the water, and then that also breached. So which caused the very big flood wave in the downstream area during the 14th to 17th June 2013. So and then the same digital elevation model can be used in the GIS with the tool known as hide above nearest drainage tool, hand tool, to give the first hand information about what are the low lying areas which can flooded if the water will raise by, for example, zero point 0.5 meter, 1 meter, 2 meter, or the 3 meter. So this model's accuracy is as good as the accuracy of the digital elevation model what we are using. And on the country level, National Remote Sensing Center, ISRO, they have generated this satellite based flood area map, and you can see the especially the riverine floods. This atlas is very useful, although for the mountainous regions still we need to work upon, but for the riverine coastal regions, this atlas can be used as a bench line data sets where the long time flood inundation and the flood frequency is available. The second most important part and also the largest user of the water is the irrigation sector. So currently, many of the irrigation projects command area network have been mapped and monitored using the satellite data. This is in the central India, in the Narmada and the basin. So this is a reservoir here, and then this is the command area of this one. So on the right hand side, what you see is the Mahanadi Burla irrigation command area, where the headwaters of the Mahanadi in this Hirakund Dam, they do the irrigation, and the topmost nearest to the dam will receive the water first as it moves downwards. So is the irrigation scheduling in this particular catchment, and the progression of the FCC in terms of redness shows that crop is growing as we are going upstream to downstream area. And due to this extensive irrigation, this area we are getting the three type cropping system, and sorry, extensive network of the paddy and the mills, rice mills. So this baseline data sets is used to compute the crop water requirement and the irrigation requirement in the command area. And the same way you can see the Jaipur, where Bisalpur Dam is used not just to the irrigation in the downstream but also to provide the drinking water. So you can see the during the peak Rabi season and post harvest how the area looks in the FCC for the Bisalpur command area. And under ISRO CWC project, there is a accelerated irrigation benefit program, World Bank funded program. So these days the funding agency, they monitor the progression of the any infrastructure project by satellite technology, and you can see whether the canal is made or not, whether water is flowing or not, if the water is flowing, whether the crop is being grown or not. So all these are linked with the satellite based observations, and you can see in the Bhuvan portal, EIBP portal. So all these data sets is available, and the two level, one is the citizen level records and other is the expert level records, so which can be visualized by the officers of the Central Water Commission or the state irrigation departments to see the progression of the irrigation network. And all these data sets is integrated into the India Voice, which was earlier part of ISRO. Now fully technology transfer has been given to the National Water Informatics Centers, NWIC, and all the surface water near real time data, it is being lively available on the Varis website. And all the atlases, river basin atlas, watershed atlas are available. And earlier it was very difficult for the general public or the academic institutes or the planners to see where these observations are being made, but using this portal you can observe and see what are the observations being made. And we have two classification system, classified and the non-classified system. The Ganga, the international rivers where water is flowing to the other countries or coming from the other countries, for example Indus, Brahmaputra and the Ganges river, they are the classified rivers where the data is not available directly until unless the permission is given. whereas the peninsular rivers, where there is no conflict except for the Kaveri River basin, they are under the non-classified category, where all Indian citizens or the authorized users can download the data freely. And next is the that up to this point, what we have covered is what are the satellite capabilities, what are the basic multispectral and radar characteristics to map water and the snow and the glaciers. And the next part of the lecture, we will see the modification of the water cycle, what we call the water balance equation, where each of the individual component, for example, for the precipitation, traditionally what we are using is the rain gauge, and for the discharge we are using the water level recorder or the gauging site. So the satellites give us the very good spatial coverage, but temporarily they may not be as sufficient as the hydrometeorological community wants. But still, the satellite fills a critical gap by giving the global observations and repeated observations. And the most difficult part of the water cycle or the water balance equation is the change in the storage. So this change in storage, whether it is due to soil moisture or due to the surface water or due to the groundwater, it is able, current generation of the satellites is able to measure them and quantify them. If you want to see the total terrestrial water storage, there is a gravity based satellite, GRACE and GRACE follow on. If you want to focus on soil moisture, there is a dedicated satellite for the soil moisture, similarly for the water level and for the snow. So we will see one by one what are these satellite systems which are used to quantify the hydrological cycle elements. And most common of water cycle is the precipitation, which drives which is the major input. So the major workhorse for this is the INSAT series of the satellites, which gives us the three set of the precipitation: quantitative precipitation estimation, hydro estimator, and IMR algorithm, which is generated by SAC ISRO, and then technology transfer has been done to the IMD. So you can see them directly on the IMD website, and also if you want to work on these products or work on the raw data, you can go to the ISRO MOSDEX website to download and do the analysis these precipitation products for the Indian region. If you want to see the global coverage, then because precipitation is happening all the places somewhere, and then we need to have the continuous observation. So what we do, we cannot have the geostationary satellites everywhere because they have certain limitations. So what we have is the combination of radar mission, combination of passive microwave and the optical and the geostationary satellites. So this GPM is one of them. So what it does, it combines the Doppler, dual frequency precipitation radar working in Ku and Ka band, and it combines the passive microwave radiometer observation to give you the global precipitation plus minus 60-degree latitude at half an hour time interval, covering zero point 0.1 degree, approximately 10 kilometers on the global scale. And precursor to this was the tropical rainfall measuring mission, TRMM, and this data has been now reprocessed with the GPM algorithm. And globally what you get, a GPM IMERG algorithm from 1999 onwards till now, and in the near real time also you can get this data. And although it may have certain error, but for the Indian region, ISRO SAC team, they have worked with the JAXA, because JAXA is equal partner in the GPM mission. They have their own algorithm known as GS map. So this combined algorithm, GS map ISRO rain, this has been generated to give you the improved satellite based rainfall, where the actual rain gauge data has been ingested into this. So other than that, these are the some other websites which you can look upon to get the satellite or the gridded rainfall data. So the other component of the water balance is the discharge. Discharge directly we may not get, but we do get the water level. And this is mostly the microwave altimeters, where instead of side looking, they are nadir looking. And in the nadir looking, due to the Earth's atmosphere, we make the correction for ionosphere, troposphere, and also for the tidal gauges. And we precisely monitor the height of the satellite, and then we monitor the two-way ranging. And then once we know the two-way ranging, we can change estimate using this non-imaging remote sensing satellite the water level at 10 days to 21 days to 35 days interval. So What you see here is the tracks of Surreal Altica, which was a first dedicated altimeter from India as a joint mission between India and France working in Ka band. So these are some of the examples which you can see from ISRO's MOSDAC and Vedas portal, and this is the time series which is available, and followed by the SWOT mission, which gives you the two-dimensional water extent, and also it is the first satellite which gives us the river discharge, although accuracy still people are working upon. So it is a Ka band traditional, this interferometric altimeter is there, and Ku band traditional altimeter is also there, and this is how it will work. It has a antenna within this 10-meter interval, so one will transmit, other will receive, and you can see here very high incidence angle of 1 to 4 degree as compared to the traditional SAR sensors. So although it will have the specular reflection, but we have onboard antenna 10-meter wide, which will directly receive the signal. And this is the basic mathematical formula where we are doing the two-way ranging. This is the fixed antenna, so that baseline is fixed. So the water height is computed using this height of the satellite r1 cos theta. Theta is the incidence angle. So you can see here, this is the right swath, this is the left swath for the Varanasi. Earlier we used to mask out the water bodies whenever we used to create the digital elevation model, but now this satellite is dedicated to generate the time series of water level. So what you see here is the Varanasi area, and we are seeing the from upstream to downstream change in the water surface elevation, and this data is available globally from July 2023 onwards, which will provide us surface water extent, elevation, and the water slope. And what you see here is the reservoir Chintal hydropower project, where in the upstream area, how the water level variations are happening, and this is the downstream area. Upstream is for the reservoir, downstream is the how the water flow is being regulated. And similarly for the one of the glacial lakes, Kedartal, how during the summer ablation time period the water level rises in this natural lake and then decreases in the winter, again rises in the monsoon, then decreases. And then this is for the Lonak lake, where it has increased, and then due to the lake breach it has decreased. And these are the two examples for the river systems. And the other component what we have is the soil moisture. Soil moisture generally from the passive microwave radiometers, so we measure it. But other than soil moistures, integrated water vapor, precipitation, sea surface temperature, sea surface wind, snow water equivalent, these are the other parameters which are measured using this multi-frequency microwave radiometers. And this is one examples of soil moisture from AMSR data. The blue represents the saturated condition, red represents the drier condition. And this resolution of the passive microwave is at 25 kilometers. So researcher wanted to have the higher spatial resolution, and longer wavelength is more sensitive to the water. So L band is considered one of the best sensor both in passive microwave and active. So NASA had generated this soil moisture active and passive mission, where we have the radiometer plus we have this active radar. So the final product would have been 10-kilometer radar and radiometer, and it worked for a few months, but due to some issues in the synthetic aperture radar, it is not working. So for the radar, currently NASA team is using the C-band data, and for the radiometer, passive microwave data of SMAP is being used to give you the global soil moisture from 2015 onwards, and this data has been reprocessed to give you the root zone soil moisture also, which is also important from the water sources point of view. The other mission, which was before this one, was ASMOS, soil moisture and ocean salinity. Again, it was having the L band radiometer. So these are some of the products which will be easily available from the SMAP website. And from ISRO web side, the reset has data algorithm has been made, and which is available at Bhunidhi. So this is the operational high resolution 500-meter surface soil moisture, which is available at every 24 days for the using the EOS4 data sets from the Bhunidhi website. and this resolution is going to increase to every 12 days at 200-meter resolution using the upcoming NISAR dataset. And the third important component of the water cycle is the evapotranspiration, which is almost covering 40 to 60% of the total water cycle. So here the basic principle is the what we call the surface energy balance. So this latent heat flux, which is represented by the ET, is function of total incoming and outgoing radiation minus the ground heat flux minus the sensual heat flux. So we use the thermal data sets, land surface temperature data sets plus emissivity albedo, and combine it with meteorological data to quantify the graded instantaneous evapotranspiration, and then using the evaporative fraction, we convert this instantaneous evaporative fraction, this ET, into the 24-hour integrated evapotranspiration on the daily basis. And this is one of the models, symmetric model mapping ET using high resolution internalized calibration, which is available in the Google Earth engine, and it is the combination of both Siebel model and for any cloud free image on a global scale, this can be used. And currently teams are working, including our team, to work on a integrated system. For example, this is OpenET, which is available to US region at 30-meter resolution using metric model, LXC. There are multiple models for ET estimation. So using the cloud platforms, this is being used, and recently it has been extended to the Amazon basin, and a few years time you may also see the Indian region being covered under this OpenET platform. And this ET is very much commercial in it caters to the commercial nature of the cropping system or the agriculture sector. So there has been private companies, the Siebel model what you have seen in the previous slide from the Professor Bastiansen. So he has opened a company and joined this Hydrosat, and they have a constellation of the satellites providing the thermal data. And on your mobile phone, if you give that this is the agriculture area or this is my agricultural field, so on demand basis they will give you the water requirement, that how much water is required to be irrigated, whether it is in the healthy condition or whether it is in the drier condition. So commercially also these data sets will be available. And from ISRO side, the Trishna mission I will show at the end, which will give you the publicly available free thermal data for such studies. And the fourth component is the surface runoff. That means how much area after getting the saturation or infiltration excess, so is flowing on the rivers on the terrain and then joining into the river system. This is example of Bata river basin, which is a tributary of Yamuna river coming from Nahan side. So the SCS curve number, soil conservation service, one of the popular methods where we use the land use and soil to combine to give you the daily basis runoff. And if it is mountainous region, the snow will also melt and give you the runoff. So for that we use the degree day approach, for example in the snow melt runoff model. And the snow cover is taken from the satellite data, air temperature is taken from the meteorological observation, and precipitation is taken from the TRMM and nowadays GPM data sets to give you the discharge in the any point from the river basin. And from the groundwater prospect wise, if you have the base layers of structural maps, lithology map, geomorphology map, hydrology map, and this has been one of the big success stories of using the space technology for the actual water identification. And for major states of India, 1 is to 50,000 groundwater prospects map has been given. So you can see here using this color scheme and also the symbology, you can see the availability, whether it is excellent, more than 200 liters per minute water, or if it is poor or the nil. So this has more than 90% to 100% accuracy. If you use this map, go with the GPS and the legend, if you dig there, so you can use this to explore the groundwater. And this has been given to all the central and the state groundwater boards and also the state water agencies by NRSC ISRO. And this is a new kind of remote sensing which is known as the gravity based satellites. So if you want to know the regional level water balance, and then if you want to resolve for terrestrial water storage or snow water equivalent or ET or the runoff, so we have these twin satellites. So any change in the position of these satellites is inferred as a change due to the change in gravity, which is inferred to the change in the mass. So this data sets is now being extensively used to see the various scenarios. For example, the groundwater withdrawal in Indo-Gangetic plains, it is happening at rapid rate. So such kind of studies. Similarly, West Antarctica is losing the ice. Greenland is losing the ice. So those loss of ice or loss of water or the gain of water is very precisely observed using these gravity-based satellites. And all these data sets ultimately contributes to the better early warning system. This is one of the examples of flood early warning system, where we do the simulation of hydrological cycle in the runoff and then convert that into using the stream flow in the unit hydrograph into the actual stream flow at each point, so through the routing system. And we use this rainfall runoff digital elevation model to do the rainfall runoff or to generate the inundation scenario. And this is one of the graphical schematics where we combine digital elevation model, soil, land use to generate the curve number, and then from that into the one of the popular models known as the hydrological modeling system to generate the event based flood hydrograph. And this is the example of the Song watershed, which this year 2025 and 2022 earlier. So in the monsoon, this area gets flooded, and this year this particular river system, one of the tributaries, it got severe floods, and two three bridges were also damaged during this simulation. And this is for the Maldevta area, 2022, and again in 2025 September flash floods, there was a damage. So this is the pre-flood image, this is the post-flood image, and this is the hydrograph as simulated by the this one calibrated hydrological model. And this can be used with the weather forecasting model. This is Dharampur area of Mandi, which unfortunately 10 it was inundated in 2015, but 10 years down the line, again this year it got flooded because this Dharampur station in the Mandi district, it is at the outlet of the near to the outlet of the this watershed, and if there is extreme event, it is very near to the river system, so usually it get flooded. And the same thing it has been done for the Yamuna river, and the simulation what we have done in the model, and this is the Central Water Commission forecast. And Beas Basin 2014-15, so these are the calibrated hydrological model, and then this calibrated hydrological model are integrated with the digital elevation model and hydrodynamic models to see the inundation scenario in the Beas River Basin. And to improve the accuracy of these models, we generally conduct the field survey, either bathymetry survey or the cross-section survey. This is some of the examples from such bathymetry and river cross-section surveys. And currently in the mountainous region, one example I have shown of the Lohanak Lake, which happens due to the retreat of the glacier. The end region, we have the pro-glacial lakes, which can be dangerous if it is the moraine blocked lakes. And one of the biggest lake is Imrat Asho in Nepal, which is increasing in the size due to the calving and rapid thinning of the glaciers due to this pro-glacial lake. And this is one of the lakes in 2013, the Choraburi Glacial Lake, which breached in 2017, June 2013. And because this area in the downstream, this is the Kedarnath town, it is having the deglaciated valley, it is loose moraine. So any rainfall or the heavy breaching of such events can cause significant damage to the downstream areas. And we have multiple hydropower projects in the Alaknanda Valley which may get affected. And these days it is now compulsory to take care of the high flood flows which will come due to such gulf. So this is one example where if you consider the normal flood depth, or if you consider the gulf, how much improvement or changes in your design structure you have to do to safely pass such gulfs. And such events, not just this one. So this is the Gomukh snout where there was a big breach which has happened in the Nila Tal, and then this debris flow event triggered the blockage of the Ganges River for few days, and later on, due to the high discharge, it was moved. And then we quantified how much erosion and deposition has happened from the satellite data, and then you can see immediately after the debris flow, there is a cyan color which is seen in the Sentinel-2 images, and also simultaneously this tributary glacier which is generating the water flow, and again this ice will be lost. In fact, it has totally broken away, and now the snout is in the particularly backside. And in 2021, there was a unique kind of disaster which happened due to the breach of a big rock fall triggered avalanche. And you can see here pre and post image in this Rontigad watershed, where the water level at this 90-degree bend went more than 75 to 100 meters. And such lakes are very prevalent in the eastern Himalaya region, much higher concentration in eastern Himalaya as compared to central or the northern Himalaya. But with the climate change and current temperature scenario, such lakes are bound to form in such regions also. And this is one of the lakes in the Bhutan region, where one of the scenario it shows extensive damage to the airport and as well as the surrounding areas. And this shows for the one lake in Leh Ladakh, where one of this Padam lake has been simulated, and the downstream area, how much area is going to be inundated. It is shown, and with the calibrated hydrodynamic models and good quality DEM, it is now possible to precisely map the extent of the flood, the timing of the flood, and the possible damages which can occur due to such rapid glacial lake outburst. And at the city level, many of our Indian cities they are highly urbanized, so the our runoff potential is much higher. So, and it is compounded by the fact that our drainages are choked with the solid waste. The natural rivers has become a drains, which during the flooding will overflow, and also it contributing to the plastic pollution and the microplastic. So this is one of the examples of the Dehradun city, where the 50 millimeters per hour rainfall for 2 hours caused the significant flooding in 2017. And again this year we have seen such phenomena in some of the catchments of the Dehradun city. And such models like the stormwater management model, where each ward can be identified that which ward will get high flash floods as compared to other areas, that can be quantified. And then under the Amrit program, under the other government central government funded schemes, you can design the stormwater drainages to take care of such high intensity rainfall, and also increase the capacity of these stormwater drains, so that the flood water can be safely moved from the city. And this particular example is a more practical solution under the this water distribution system modeling. So each major river system and the ward has been simulated in a 24-hour simulation. The red areas shows where we have the negative pressure. In ideal water distribution system, all users should get the water, but if it is negative, that means sufficient pressure is not available. So such kind of simulation and the models are now mandatory under the Har Ghar Jal mission and Jal Jeevan mission. So the water planning departments of various states and the cities now you use such GIS and remote sensing based models to generate various scenarios and do their planning, so that you have the sufficient water to all the citizens. And also the the wastage of water can be saved by better planning using such tools. And in future, ISRO, we have this approved mission of ResourceSat 3 and 3A, where you have the wider swath data sets at a higher resolution, and also you will have the cartography mission with the elevation information at 1.25 meter resolution with revisit of 4 days. And GNSS generally used for the location, but it is mostly working in the L band. So we have this hydro GNSS mission, which will be giving the permafrost, biomass, soil moisture, and inundation using the L band data sets as a from the GNSS reflectometry. And from the thermal domain, we have in the next few years ISRO GANES mission in the thermal domain, which is the key workhorse for the agriculture, water management, ecosystem services, cryosphere studies. And NISAR is already in the orbit from July 30th onwards, and the data sets soon will be available in the Bhunidhi portal. SWOT is giving us the very good quality data from July 2023 onwards. And in future, we have a dedicated altimeter mission, popularly known as Copernicus Polar Ice and Snow Topography Altimeter, which will give us more and improved altimeter data to quantify the snow depth, ice thickness over the polar regions and the mountainous regions. So, with this, I complete my overview lecture on the remote sensing GIS applications in water sources and hydrology. And if you have any questions, you can send my in these two emails. I'll be happy to answer all those questions. Thank you.